I am going to share a set of slides with you here. Okay, so what I'm going to be talking about today is this new communications technology known as 5G. I'm going to try and give you a few ideas about how this technology will work, what it's designed to do, and what we might look out into the future. So this 5G is a revolution, right? You've heard the advertising slogans, you've been watching advertisements for, on various sort of TV networks and said, oh, the world's going to change. And somebody provides you with this wonderful diagram that says, look at all this communication capability. I could actually give you a talk with all this kind of flash and bang. Actually, I'm not going to do that. I'm going to try and think a little bit more carefully about what this might be doing and how we might get to this particular revolution. So I think it's not unreasonable for there to be hype. I think every time we have a change in communication technology that's regarded as a revolution, okay, the proponents will suggest that this is indeed a revolution, but there will be many that fear change. And 5G is no exception at all. So let's step back from the hype for a little bit and think a little bit about what communication might be. You know, fundamentally, it's a human desire. You might even say that it's an evolutionary imperative, because from an evolutionary perspective, we need to alert each other in the community about recent events, but we'll also benefit greatly from accumulated wisdom, for ways to store and access accumulated wisdom of the community. And over centuries, communication technologies have dramatically changed societies. And I think in the long run, this has generally been for the better. So how might we view 5G in these sort of settings? And what are the technologies that we need to do to be able to achieve this vision? So if you think about the evolution of communications, think about interpersonal communication. We talk to each other. We wrote letters to each other. Then we started to talk to each other on the telephone, and then maybe we would send emails to each other as well. And how do we communicate as a community as a whole? Well, there was the invention of the printing press, which led to the written word, books, newspapers, and these enabled repositories like libraries. As radio and television came in as a technological revolution, and this enabled the recording of various sorts of archives. And then starting, perhaps in the 70s, late 60s, the ARPANET, and then eventually the internet provided this really easily accessible repository of knowledge, and it has to be said, a repository of opinion. So what's the common feature here? All of these things are only available in one place. If you want the newspaper, you either have to have it delivered to you or you have to go out and buy it. If you want a book, you have to go to a bookstore and buy it. Well, okay, perhaps before Amazon. Or you have to go to the library and borrow it. There's a geographical restriction to all of these forms of communication. So what's the goal of wireless communication? It's this ubiquitous ability to communicate. So if you go back, maybe we had portable radio. So you listen to an AM transistor radio. That was a way for us to receive mass communications in a ubiquitous way. We had pages. Then mobile telephony and text messaging developed, and then eventually mobile connections to the internet. And the great thing about where we are now, these current technologies bring all of this stuff together in one device. So we have this ubiquitous ability to communicate person to person. We also have this ubiquitous ability to access information, opinion, and entertainment. Okay? And something that is developing for us is we have this opportunity for ubiquitous interactions with the way our society operates. We can interact with our banks, with our government, with a variety of societal organizations ubiquitously. We don't have to line up in a queue to go and do that. What we are also developing is this ubiquitous ability to process information, and something is called ubiquitous computing, which I'll get back to in just a minute. So what are the impacts of this ubiquitous communications? Well, I'm just going to highlight a few, and these are going to show that it's not always a uniform good, but it can be good for us. So one of the things it enables is organization or self-organization of movements for societal change. So what that does do is it enabled the Arab Spring, but it also enabled ISIS. In Africa, what this ubiquitous ability to communicate enabled was an organization called M-Pesa, which is a branchless banking organization that enabled banking and the societal benefits of banking to be spread through Africa without the need for branches and a variety of other things. Unfortunately, that thing was also a monopoly. And as any economist would tell you, there's a moral hazard to a monopoly, and that moral hazard realized itself in that case too. For those of you who like to read The Economist magazine like I do, in this week's issue, there is a survey that correlates the level of distrust in government with the rise of mobile communications. Now, how you might view this, maybe providing more information to a society enables a society to observe how the sausage is made, and maybe they don't like to see how that sausage is made all the time. What you will also see is that the level of distrust in authoritarian regimes is also increasing with mobile communications. That suggests that maybe this is a platform for other sources of information that might be of interest. Okay, so like a lot of previous changes to communication technology, we'll keep going back to the printing press. There's an element of personal choice in terms of how we use that. Unfortunately, some make the choice, take the opportunity for this change in technology to exploit human weaknesses in others for their own benefit. And I think this is something that we need to think about as we introduce these technologies to our communities. I talked a little bit about ubiquitous computing and this idea that we have in our phones, we have this ubiquitous ability to be able to process information. Now, this was a term that was coined by Mark Weiser of Xerox Palo Alto Research Center, one of the most famous parts of the Silicon Valley setup. Okay, the fact that we have a mouse on a computer and that we have a Windows-based system for interacting with our computers is something that came out of Xerox PARC. But Mark Weiser, who is pictured here, envisioned a third age of this ubiquitous computing as a third age of computing after the mainframe of the 60s and 70s and the personal computer that we have on our desks. I think it's important to have a look at this quote that he said at the time. Next comes ubiquitous computing, or the age of calm technology, when technology recedes into the background of our lives. Okay, what he said was that the purpose of a computer is to help you do something else. Okay, and along with John Seely Brown, he further developed this notion of calm technology, and it's this technology which informs but doesn't demand our focus or attention. Okay, and I think the technologies that we have and the technologies that we're developing in 5G do have the opportunity to enable you to do something else. They do have the opportunity to be genuinely calming technologies that provide you with greater opportunities to do other things. Okay? What has happened is that some who have developed components of this technology have indeed demanded your focus or attention. And those of you who've watched the next Netflix documentary, The Social Dilemma, will see that there is in fact a whole attention economy. But we can choose to participate in that or not, depending on how we think about those things. But I really came here to talk about 5G. So what are all these Gs? Well, I'm going to take a little bit of a revisionist history. I think academics want to do that kind of thing. But this is what the Gs look like now. So researchers, mostly in academia, continuously develop ideas on how to advance mobile communication technologies. And I've just spotted my first typo in my slides there. But we're continuously working on different ways in which we can communicate. But about every 10 years or so, members of industry, academics, and futurists sit down and imagine what might be possible in 15 years or so in terms of communication technologies and what we might be able to do with it. And they set down some goals, and these goals drive technology development as companies compete to have their technology entrenched in the standards for the communications. So if you are a communication technology company, the holy grail for you is to have the standard for communications built around a particular technology that you have developed. Okay, then you earn 10 cents or 15 cents on that technology that goes into every cell phone and every base station and every piece of communication equipment, and that is something that brings great value to your company. Okay, and so each generation happens about a decade apart, and there are multiple incremental releases of these standards that happen as things develop. So what were the goals in the past? On the left-hand side, we have a first-generation cell phone. This is classically about the size of a shoe, okay? And then as we go down the hill in this diagram, you will see a second-generation cell phone, some early third-generation cell phones, and right down the bottom right here, we have something that looks like a BlackBerry, which was really the quintessential third-generation cell phone. So what were we thinking about when it came to dealing with these systems? So the first handheld mobile phone call was from Martin Cooper, who is pictured there reenacting the event. And you can see the size of the phone that he is using to make that call. And he made that call to Joel Engel, who was working at Bell Labs, which is a competing company at the same time. Now, according to legend, Martin gently informed Joel that he was calling from the street between 54th and 56th Street in New York City. And he was calling him from the street on a new mobile phone. According to legend, there was silence at the other end. And Joel Engel has denied any memory of that event. Trauma is often removed from our brains as a natural defense mechanism. Maybe that's what happened there. So this phone weighed over a kilo, provided 30 minutes talk time, took 10 hours to charge. So then in the early 80s, a version of this phone became the first commercialized mobile phone. And this used analog voice technology. So this is essentially like versions of conventional radio systems to send voice information. If you look at the price of a cell phone in those days and convert that into to today's dollars, Those phones are worth about $11,000 each, and that's $11,000 US. So the second generation that happened in the 90s involved a conversion from not analog technology, but digital technology. So converting voice signals into a stream of zeros and ones. And that enabled us to combine not only voice, but some text messages as well in a similar sort of way. In the third generation, in the 2000s, these became a little bit more ambitious. Not only voice and text, but we wanted a little bit limited ability to go out to the internet and maybe bring in some information from the internet. And an extremely limited ability for that person to be able to go out to the internet and send information out to the internet. And then the fourth generation, which is starting in the 2010s, again, voice and text are just sort of permanent features here. But now the idea was genuine internet connectivity, including multimedia like this. So sometimes the goals are so ambitious that we were not, as technology developers, we weren't able to develop technologies to realize these goals fast enough. And you may have heard of 3.5G and 4.5G type standards. So there are sometimes we need to graduate these things in a little way. You may have heard of long-term evolution, which is sort of the current standard that we are dealing with. Even when we tried to do that, we wasn't able to realize the goal, so we had to develop a long-term evolution advanced, or LTEA, that is now the fourth generation standard that we was the dominant, is still the dominant technology today. So what did we, so 10 to 15 years ago, what did people say? Okay, here are the great things that we would do with 5G. So what they wanted to do, first of all, is to enhance this sort of mobile broadband experience. So essentially, this is a lot more than what we already have. So 100 to 1,000 times the data rates. For those users that are in the bad places, we still want to be able to give you 100 times the data rate that you can get in the good places right now. So if you're stuck behind a building or your cell phone is dropping out now, we want to give you 100 times the best data rates that are available now. We want to be able to serve more people in different areas. We want to be able to reduce the energy consumption by about 90%. And we want to reduce the amount of wait time that you have. So one application of this that I find quite compelling is emergency response from an ambulance. So you're in an uncontrolled environment that you're not tethered in any way. And an an emergency medicine technologist comes to you, looks to examine you, and sticks on what would be an augmented reality headset. So what this person will be able to do is to see you and see exactly what's going on, but at the same time, through this wireless connectivity, will be able to have information displayed on top of your body, on top of the image of your body, that tells them the sort of things that could be going wrong, okay, and the sort of tactics that you might be able to fix. So say you have a slash wound across a leg, that might be nothing at all. Or that may have cut one of the major arteries and you may be minutes away from death, okay? Now, current EMTs can see this, but by having this augmented reality system on, then not only can we match the anatomy to what is going on, but you can have short-term life-saving measures being displayed to the ambulance technologist right there on the spot. Okay, so if your condition happens to be unusual, you can have expertise from emergency medicine just displayed on the screen as this person is looking at your body. Okay, so that needs low latency to make sure it's fast, We need massive data rates to make sure that this picture is useful to the person who's trying to save your life. And these are one of the sort of applications of this kind of technology. Arguably, this is all quite interesting. You know, a little bit more and a lot more than what we already have is kind of interesting, but it's not necessarily enough to generate huge excitement. So what's generating the huge excitement? It's probably the other 5G goals. So these are things like mission critical communications. There is a goal for the internet to be able to respond to you just the way that this table responds to my finger as I touch it. So in milliseconds, can the internet respond to things that is going to enable me to do things that Tony was mentioning, self-driving vehicles, industrial automation? We need these systems to be able to respond that quickly. Okay, you notice that this is only about a 15 times reduction in the latency, which is nothing like the 100 and 1,000 times increases that we were talking about elsewhere. But this is actually much harder to do. The other thing is massive connectivity. So the ability to be able to connect probably 10,000 times the number of devices, okay? And devices that may last for 10 years on the power provided by one battery. And these are the sorts of things that are going to enable us to monitor our environments, maybe make better use of agricultural resources, maybe help us manage traffic, and maybe help us manage the environment better, all in a way that is going to be at low cost because it's using a common infrastructure. So the idea is you want to do everything with one technology, okay? We've had specialized machine type networks before, okay? Now we want to be able to use the flexibility and the scale of cellular to help us. Now this is where one particular place where the security of communications is going to become a particular problem. We've had some big events that where problems have occurred. Target notoriously had their air condition monitoring system connected to their payment networks. So suddenly the air condition monitoring system started to take a great interest in the credit card numbers of their clients, which is an unusual thing to happen, but that's how credit cards were breached at Target. There's a famous video in 2015 of hackers using the entertainment system in a Jeep Cherokee to put the brakes on, change the fans, and run the car off the road. Now, it was a controlled experiment, but it was particularly well done. And an earlier example was that in Iran, a lot of their nuclear reactors and nuclear centrifuges suddenly stopped working after USB keys were found in the car park and people plugged them into their networks. So this has been done in a variety of different ways. Okay, but the security will be something we really need to think about. I really want to talk about here in terms of the technical content here is to try to get you to give you a little bit of a hint as to how these networks actually work. So the basic setup of a cellular network involves partitioning the geographical area into particular cells. And within each cell, any user that's in this environment will connect to only one of these base stations. Okay, and what you can see, what you may be able to see here in the boxes is each one of these cells is labeled by an F1, an F2, an F3, or an F4. And what we're really worried about is how much interference each communication receives. And to do that, we operate, say, this cell here in the top left corner in one frequency band, and the one next to it to the right in a second frequency band. and then we reuse the first frequency band on the third one over the right. So anywhere where people are using the same frequencies, we want to separate them geographically so that they don't interfere with each other too much. Okay? We also want to separate in frequency the communication from a cell phone to the base station and the cell phone from the base station back, again, because we don't want that two-way communication interfering with each other. Okay? These are not the optimal things that we can do, but these are the ways that we manage complexity to make cellular networks work. So how are we going to get there, or how really did we get there to meet these massive goals that we had for at least the mobile broadband part of 5G? Well, we talked to this guy, Claude Shannon, who in 1948 tried to understand what is information. Because once you try to understand what is information, then that helps you understand what it is that you need to communicate. Okay? And this is a picture from Shannon's original paper. And he tried to understand what is meant by communication. Okay? At least in communication in a digital sense here. So on the left, we have a source of information, and we have a transmitter. And this transmitter processes this source information any way it likes. And then we send that signal out over the air to a receiver on the right-hand side. And we presume that this receiver can do anything it possibly can to be able to work out what was sent. And then we send that information to the destination. And in between times, that signal is corrupted by noise and interference and other sorts of effects. And what Shannon showed quite remarkably is that there are data rates at which you can communicate over this channel and have no errors. So at the time, this was thought to be heretical, is that the only way we could send information with no errors was to send nothing. And what Shannon showed, that actually you can communicate without any errors up to a certain amount of data rate. And then beyond that, it's impossible. Okay? And that led to this formula that's here in blue, which is sort of the E is equal to MC squared formula for my field. And this tells us that how much you can communicate is less than a formula which consists of the bandwidth in which you're operating, so how much spectrum you have, plus a logarithmic function of 1 plus the SINR, which is the ratio of the signal power that you receive divided by all the noise and interference that you receive. Okay? And so this is a fundamental limit. It has no constraints on technology. It's just this, if you use technology in the absolute best way you possibly can, this is what you can achieve. Okay? And Shannon argued that there were many ways that you could do this, but he never actually went and found one himself. Okay? And by the 1970s, no one had been able to find one. So this is 1948 to 1970. No one had been able to get close to this. Academics even asked, is the field dead? Or maybe is the field a little bit inbred and not thinking outside the box? And then some outsiders came in and hacked away at something and got really close. And what they did was that they were able to use the randomness that was inherent in Shannon's proof that this was possible, but they were able to structure that in a way that manages the computational complexity of actually doing it. Okay? And since then, we have reimagined a number of things, so we can actually operate at this with this formula at the top of the page. We can actually build systems that operate at these limits. So this is now really fabulous guidance for what we should do. So what does this formula tell us? Okay, so let's try and pick this apart a little bit. We've got rate on the left-hand side. We've got bandwidth here. We've got a log function. And inside the log function, we've got a 1, which we can't do anything about. And then we have this fraction. And the fraction includes the channel gain. So that's the propagation and how much energy gets lost between when I transmit from here to you. The transmission power, which is how much power I transmit to you. The interference power, which is how much power we get from everybody else interfering with us. And the noise power, which is depending on the receiver technology. So once we've fixed things in terms of which frequency bands we're going to operate in and which receiver structures we're going to use, we can play around with the bandwidth, the transmission power, and the interference power. So let me just look at the trends here. So on the left-hand side graph, we have, on the x-axis, we have bandwidth, on the y-axis, we have the rate. So you can see that as we increase the bandwidth, the achievable rate goes up quite fast. In the middle figure, we have the relationship between transmission power on the x-axis and rate. And you can see because that transmission power is inside the log function, to start with, we get pretty good value for money for using more power. So things go up really fast here on the left-hand edge, but things slow down in terms of how fast they're going up on the right-hand side. And finally, on the right-hand side figure, we see as the interference power increases, okay, the amount that rate at which we can transmit at goes down really fast. Okay, so and we have to think about if we transmit at high power to make us look good in terms of the middle figure, we're going to be causing interference to other people, which is going to make them look bad like the right-hand figure. So what we have to do is we have to build systems that can balance these things out for us. What about the bandwidth? So it looks like the more the better. So the wider spectrum we can use, the better. Okay, but the more we take for us personally, the less room there is for other people. Okay, and we also have to worry that the channel gain changes with frequency. So in traditional cellular, we use frequencies that are around a gigahertz. Okay, what is being planned for 5G is to use higher frequencies. Okay, so if I take up a chunk of 20 megahertz of bandwidth around 1 gigahertz, that's taking up quite a lot of the spectrum just for me. If I take 20 megahertz of bandwidth at 20 gigahertz, that's taking up much less of the spectrum. It's leaving a lot for everybody else. So that is helping us make more space in the spectrum for everybody to use. Okay, these millimeter wave, particularly these millimeter wave ones, they result in small antennas, which gives us lots of opportunities, but the propagation characteristics are really bad. We can't really communicate from outside to inside in these bands, so we need to look at other bands. Another thing we look at is the channel gain. So how far apart are we? Okay, so if you look at the basic physics of propagations in free space, the amount of power that you receive goes down like 1 over the separation squared. In other cases, then in urban settings, things go down much faster. So that suggests that we need to pack these base stations in much more closely so the distances over which we communicate are much less. And there are a variety of names of cells for that. So here we have a picture of this. We might have this large traditional cell with a base station in the middle that's communicating in normal ways. But you see these smaller cells where people are communicating over smaller distances, so therefore can achieve higher data rates. But we have a massive problem now in the sense that all of these little cells might interfere with each other and with the big cell. So we have a large computational problem to be able to manage the interference between everybody. Some of you may know that radio propagation is better at lower frequencies. We still do have a few global radio stations that use really long wave radio that can propagate around the world. When BBC has a long wave service that propagates around the world. So this suggests that while we're going up to high frequencies to try and get more room, we might want to go down to lower frequencies in order to be able to have better propagation characteristics, a better channel gain. Okay, and that's why some 5G operators are looking to come down into the broadcast TV bands in order to get those better propagation characteristics. And the Nobel Prize, people who won the Nobel Prize this week for economics, they created an auction system that encourages the people who own those TV bands to sell them to operators who want to operate mobile communication services. So part of the application of their prize-winning work on auction theory is to do that. Here we have a system of a person tapping 2 balls into a lake. And you'll see waves emanating from those 2 balls. But you'll see that those waves are strong in some directions, and those waves go to 0 somewhere else. So can we recreate this with cellular? And the answer is yes. With using multiple antennas at each base station rather than just one, so rather than transmitting in all directions, we can design systems that focus our energy on the users that we are looking to send information to, and we can make sure that we don't send interfering information in the direction of users that are users that want to use that same area of or those same system resources. Okay, and these beamforming systems not only improve the channel gain, reduce the interference power, but they also have a multiplier effect out the front that enable us to really improve the behavior of the system. The last thing that I will say is that computing technology and advances in mathematics and computer science are enabling us to make decisions on how we allocate these different resources to different people in a way that is dynamic, rather than traditional things where we had to avoid interference statically, and that resulted in many of the system resources being unused. Okay, so the idea now is to, rather than statically avoid interference, we're actually going to absorb a little bit interference to make the system work better for everybody. Okay, so what happens when we start to move to these new models? There's not just more of the same. Okay, the question is, do we have to throw out all this insight, or is there something that enables us to keep going? Okay, so the nice thing is that we can extend Shannon's theory so it looks very much the same. There's just a small penalty if you're communicating over short time frames. There's just a small penalty that we need to add in and work with. So we can apply the same sort of mathematical insights to get guidance as to how we communicate. Okay, when we're looking at massive connectivity systems, now we have to rethink. Each time your cell phone connects to a base station, it has a sort of contract with that base station. Okay, when we have 10,000 or 100,000 devices, we can't make those contracts, and all these users have to transmit randomly. In fact, most of them are going to be so low energy, they're going to be asleep most of the time. They're going to wake up, send some data, and go back to sleep again. It's a totally different way to manage things, but we're learning how to use these insights to help us along the way. The one thing that gets lost in a lot of this hype about 5G is what's happening to those who are missing out. Okay? For those who miss out on connections to these information resources, wireless connectivity is generally cheaper than any other way to connect to them, but it's still a significant financial risk and something that is really something that is going to need attention from us as a society as a whole. So what's the outlook here? So We're looking to provide a ubiquitous ability for people to communicate, to access information, opinion, and entertainment. And it is really transforming the way we do things. And we're able to enhance all of these things by understanding fundamental models for information, fundamental models of wave propagation from physics, some mathematical insights, and advances in computing and sensing technologies. So, like many communication technology advances of the past, those with knowledge may seek unreasonable influence over those who do not. And I think we need to emphasize, what this emphasizes to me is the value in nurturing in each other both the capacity and the confidence to think independently so that we don't allow ourselves to be taken over. The ubiquitous connectivity of machines does offer us a wonderful ability to operate our society with far less impact on the environment. I think adding sensing into agriculture is going to dramatically reduce the environmental impact of agriculture in the way we operate that. But what this does is it really makes it important for us to incorporate security into the basic design of the network systems. It may exacerbate disparities in job opportunities, which is, I think, something that we need to address as a society. And I think it encourages us all to think about all of us as we envision what it is that we can do with these technologies. I hope that's given you a little bit of an outline of where we are and a little bit of insight as to how some of these things have evolved. And I would be very happy to engage in a discussion with you as to the things that you would like to have learned here that were not on these slides. Thank you very much.
Question number 1. How feasible is the goal of reducing energy consumption given the expanded use of communication technology that 5G will enable?
So the secret is, so the goal of that energy reduction is to be able to do what the energy cost of doing what we currently do will go down. So I think this energy cost reduction is because we will look at that formula that Shannon had, okay, and we will be able to try to operate close to the limits that he promised, then we will be able to reduce the energy that we expend in doing what we currently do. The challenge for us is that we're actually also going to try and do more. And for communication operators, I mean, one of the big impediments to 5G is the cost of buying the equipment to be able to put the base stations out there. However, that's less than 50% of the cost. The energy cost of operating these things is enormous. So it is definitely a challenge, just the same way as all the energy we spent on doing Bitcoin mining is a terrible environmental challenge as well. But the key to achieving that is to operate these systems at close to the communication efficiency, which reduces the amount of energy consumption.
Okay, thank you. Another question. Increased connectivity raises the issue of privacy as well as security of information. Example, the Internet of Things. Will privacy concerns create greater resistance to the use of 5G connected things?
So I don't think it will change our cell phone habits. I do think the danger is in the Internet of Things type setups where you have really cheap devices where manufacturers may skimp on security components in order to be able to build a cheap device, okay? And which is why, you know, the air conditioners in Target stores started taking a real interest in the database of Visa card numbers, I mean, this is a problem, and I think the idea of 5G is particularly the Internet of Things part of 5G is that the security is embedded in the standard. So the goal of the standard is not try and find a way to communicate as best you can and then add the security on afterwards. The security is going to be embedded in the design of that setup. So that's where we hope that those who are working in security are able to think creatively enough, or able to think more creatively than those who would look to break the security. And that's the intellectual challenge on both sides, is that battle of thinking creatively.
Okay, thank you. Bell and Rogers both have 5G. Do you need 5G compatible devices? And what are they providing users with today?
Okay, so the first part of that vision for 5G that I talked about was doing better for what we already have. So yesterday, Apple introduced new phones that have 5G on them. In May, I think Samsung introduced phones that have 5G on them. Bell and Rogers offer 5G service. It's essentially that more of the same kind of service. So if where you travel, you are happy watching the Leafs play on your cell phone, and you think the quality of the video that you watch as you wander around somewhere is okay, or drive around somewhere is okay, 5G is not going to offer you an enormous amount. If you are in environments which are really crowded, where it takes forever to download email onto your device, then if you have a 5G device, you will have a significant advantage there, because not only is the technology able to handle more data, there won't be many people using it because all the rest of them are on 4G service. So there will be an early adopter's advantage there. But if you are happy with the mobile phone experience that you have now, all the 5G is going to do at the moment is offer you better quality of what you've already seen.
Okay, that's good. Are there any dangers to human health caused by this technology?
So this is an area of complete lack of expertise on my behalf. However, the radiation, this is not an ionizing radiation, so it's not like an X-ray. And even when you go up to millimeter wave bands, which are higher frequencies, that's a non-ionizing radiation. The towers that we had for communicating wirelessly across Canada in the 50s and 60s, they use those microwave type bands. The challenge is now you've got a transmitter next to your head rather than on a tower that is 20 meters in the air. I mean, this is a topic that has been significantly investigated. I'm not aware of any medical grade studies that suggest that there is significant danger.
Okay. Comments on fiber versus 5G and cost to the consumer.
Okay, so one of our local telecommunication companies, probably not the place for me to say who, dug fiber down my street over the summertime. And what that will give me wonderful data rates down my street, uninterrupted by anybody else on my street who is using that data. But it cost them a lot of money to dig the holes. The labor costs of digging that hole was huge. That service provider could have put up a tower and put 5G service on that tower and offered a few people in the neighborhood the same kind of data rates. But when it rained, those data rates would not be quite as good. And but it would be a lot less cost because they wouldn't have to dig this fiber down the street. And I think where this really matters is connectivity in underserved areas. So in the north of Canada in particular, it's just not viable to dig fiber. They're thinking about putting fiber along the railway tracks, but there are some places that are a long way away from railway tracks as well. So in those settings, having a sequence of repeater towers is possible, but even that is really quite expensive. So there is some talk of using satellite as well, and running 5G over low Earth orbit satellites that may be able to provide coverage up there. But those are, in terms of cost to the consumer, it's the labor cost that is of installing this that is the biggest problem. But once you have fiber, it's really reliable. With wireless, there's still there's still fundamental variability in that.
Okay. Another question is interest, like many Canadians, is knowing which of our carriers use 5G from China.
So this is a very interesting topic. I do not think that the Canadian government has made a pronouncement as to whether they will allow the use of Huawei technologies. Huawei technologies are used extensively in Canada's 4G networks. So you have been using Huawei technology. The likelihood is that you've been using Huawei technology in a variety of settings for some time. The key thing here is that now Huawei technologies are now the dominant component of a number of the standards. And Huawei's Global Wireless Research Center is in Ottawa. So there's a lot of that technology is developed in Canada. But the corporate structure in China does have an interpretation that suggests that the interests of the Chinese government are subservient to the interests of the companies, and that's the real question. And because of the way that is legislated, there is a fear that the Chinese government could, on the quiet, pull the lever on that subservience and have those companies collect information. It's a very difficult political question to resolve.
Another question, do natural events like weather interfere with 5G? A new TV series, Cobra, focuses on a solar event shutting down all power in the UK.
Ooh, okay. So let me start with the easy stuff. When you're watching TV, if you watch broadcast TV, not cable TV, but broadcast TV in a snowstorm, sometimes not all that great, right? And some of the best, those are some of the channels that have the best propagation characteristics that we know. So those, those are bands that the cellular operators are trying to use in order to be able to get good propagation characteristics. You'll have to put up with low bandwidth, but you'll get good propagation characteristics. Okay, so it will, those low frequencies will provide service as good as or better than broadcast TV when it was over-the-air broadcast TV. In the millimeter wave bands, there are some bands that are absorbed by water. And so one of the problems that was in early wireless communications to houses was that you have water and leaves on the trees. So you get really good propagation characteristics in winter, but really poor propagation characteristics in summertime because the leaves absorb a lot of the power. And one of the problems was that in the wintertime, the propagation is so good that you start to interfere with people that you don't interfere with when the leaves are on the trees, because the leaves absorb all those things. So managing the network in those millimeter wave bands is quite hard. You can even take your cell phone and sort of turn around like this, and the propagation characteristics will change. So those things are there, and that's why 5G is designed to work in multiple bands, so that you can, if one band starts to behave badly, you can operate in another band in a reasonable fashion. Not quite as great, but a reasonable fashion. The bigger question of solar influence on radio networks and power networks, that is a problem. You know, and you know, it is not inconceivable of a large solar event taking out the power grid. Okay, and if you take out the power grid, you lose power to the base stations. So do you provide battery backup in the base stations to be able to run those base stations even when there's a power outage? Yes. How long should that battery backup be? 1 hour, 1 day, 1 week? Those are the challenges. I mean, one of the things that people are working on is cellular for disaster relief. So there's a sort of related thing. If you have a natural disaster that takes out a lot of your cellular infrastructure, you can throw up a drone, and either a helicopter drone or a plane to go to fly around and act as a base station. So we're building technologies to be able to do that, so that so long as all the devices have battery power, you can throw up this drone and it will work like a 4 or 5G base station and be able to replace that in the short term. But yeah, major solar events, I think, are going to be trouble all around if they come to pass.
Here's a follow-up to the 5 gig political concerns. Someone says, I gather some companies have already started installing 5G. I was told by someone in the business that they have done so with some Huawei components already. Is this true?
That I am not close enough to what the companies are doing to know that. I do know that there is plenty of 4G Huawei equipment. So previous generation wireless, there's plenty of Huawei equipment across Canada from 4G. I don't know who is buying what at the 5G level. But I know in Britain, where they did have a very mixed decision in terms of the technologies, where they allowed service providers to use Huawei equipment for local parts of the network, so sort of from cell phones to base stations, but they did not allow them to use Huawei equipment in the core network where all those base stations start communicating together. Yeah, so I unfortunately, I don't know the answer, but I would not be surprised if some of the vendors are doing that. The price of Huawei equipment is significantly cheaper.
What does it mean when 5G shows up on their phone rather than LTE?
Okay, so LTE is the 4th generation system. And so this will give you, again, a reasonable experience. So you might expect to get reasonable quality video on a cell phone. And be able to move around at walking or even slow driving speeds and still be able to get reasonable quality video on your cell phone. What will happen when you see 5G is that you should expect a quality, or the data rates that you would expect to receive would be probably 100 times higher, 10 to 100 times higher. And so what you would expect is far higher quality video experience. I think, you know, it would be difficult to tell the difference between the audio experiences or the internet download experiences. I think those would be reasonably similar, but I think where you would notice it would be video experiences.
Okay, so I think that helps with the next question. Wanting to know if you need a special phone to access 5G, or will it work on current phones?
So it's a new standard, so you will need a phone that is 5G capable. So there, in each phone, there's a transmitter and receiver, and so most of the phones that you will have bought now will have a transmitter and receiver that know the language of 4G. So they know how to arrange data so that a 4G receiver at a base station can understand what they're saying, and they know how to arrange the data, how to interpret what a 4G base station is saying, so they can extract the data when you're getting messages from the outside world. And I think, so if you think about this as being a language, then, you know, your 4G phone understands the language of 4G. If the 5G is a new language, you need to have a phone that will understand that language to be able to take advantage of that. But 4G is going to be there for 20 years from now. So it's not like your phone is going to be instantly obsolete. It just may be that your buddy gets a slightly cooler video than you do, and that might be something that you think about.
Okay, thank you. That's all the questions.
Thank you very much for your questions. I hope that there's some kind of interest in the fact that we have, amongst communication engineers, we have a equation that is as fundamental as E is equal to MC squared. And the fact that that is the equation that really provides guidance to us as to how to build sensible systems. So it's nice that, you know, something that somebody who thought differently from everybody else, you know, 60, 70 years ago, you know, his influence is shaping the way these technologies are being built today. All right, thank you very much.